All right, good morning, everybody. Welcome to the third day of the workshop. The third day, as you will have seen in the program, will be dedicated mostly to quantum algorithms, and it's a great pleasure to have as our first speaker, Ashley Montanaro from Bristol University and Phasecraft, who will start with an overview of quantum algorithms. Thanks, Ashley, and the stage is yours.
Great, thank you very much. So thanks everyone for coming along to my talk, and thank you as well to the organizers for giving me this impossible task to start the day with, because I think, as will become clear from my talk, if it's not clear already, like it's really impossible to do the field of quantum algorithms justice in one overview these days. There's a gigantic amount of really interesting work, and I'm only going to really be covering a tiny fraction of that. And also, you know, I realize there are some real experts in this audience, as well as some people who are maybe new to this field. So I have to apologize to the experts that this talk will be extremely non-technical. There's very little in the way of theorems. In keeping with the sort of near-term feel of this event, there are a few sort of actual numbers in there rather than sort of just asymptotic kind of big O kind of complexities. So maybe people will like those. But please do feel free to ask questions if you'd like me to go into any more details about anything. Although, you know, in many cases, I'm talking about other people's work, so I may just not know the answer if you do ask the questions, but I will do my best.
But the audience probably.
The audience may well do, yeah, exactly. So I'll just pick on individual people in the audience. Excellent. So, okay, so just to kick things off, I mean, I think maybe it's already clear to everyone in this audience that a quantum computer is not just a faster classical computer. In fact, you know, it may be a slower than a classical computer when thinking in terms of like clock speed and sort of raw number of instructions that can be executed per second. If we want to do something interesting using a quantum computer, we need to develop a quantum algorithm for that problem that we're wanting to solve. And, you know, the field of quantum algorithms aims to do that. And, you know, it can be helpful to think about dividing these algorithms up into different categories. I guess, you know, really there should be sort of applications rather than algorithms, but, you know, most of the applications of quantum computers tend to fit into one or other of these categories. For sure, not all of them, but many of them do. And I think, you know, that's sort of the rough taxonomy I'm going to take in this talk today. And I guess, you know, the thing about quantum computers and quantum algorithms is that these are sort of special purpose things. They're algorithms for solving particular tasks rather than just, you know, speeding up arbitrary computations. But the important and interesting thing is that many of these tasks are actually very important for real-world applications. So, for example, we have quantum algorithms for simulating quantum systems, which are exponentially faster than our best classical algorithms for accurately simulating quantum systems, which is really important because ultimately the universe is quantum mechanical. And if we want to model the universe, then we need to model the quantum mechanics in it. We have, like, famously quantum algorithms for breaking cryptographic codes. Some of the, you know, most important early results in the field of quantum computing. We have quantum algorithms for solving hard optimization and constraint satisfaction problems faster than analogous classical algorithms. Grover's algorithm is perhaps the most famous example of this phenomenon. We have quantum algorithms for addressing high-dimensional linear algebra problems, such as the famous Harrow-Hasidim and Lloyd algorithm. You can see that there I've put a question mark next to the exponential speedup because these algorithms are very interesting in that sometimes they appear to deliver an exponential speedup, but then once one goes through the details, it turns out the exponential speedup kind of vanishes. So that's an important thing to check. And also there are quantum algorithms which, you know, may solve problems better than our best classical algorithms, but perhaps we can't prove this. They may be doing some sort of interesting things which, you know, are worth studying numerically. Maybe they deliver higher performance on some sort of instances we see in practice, but maybe it's difficult to analyze them, difficult to prove that they're correct. And, you know, one example perhaps of this category is the quantum approximate optimization algorithm, which I guess we'll hear a lot more about from Eddie Farley later. But I mean, and I guess maybe I'll make the case a bit later that this may actually sort of move up the list in some sense, in that sometimes we can prove bounds on its performance. Okay. And I don't know if any of you have seen this resource, the Quantum Algorithm Zoo, but it's very nice because it lists hundreds of papers on quantum algorithms. Last time I checked, it actually hadn't been updated for a little while. I think it's probably becoming, actually impossible to keep it updated because there's this sort of onslaught of new work on quantum algorithms. But you can go to that and see already hundreds of different algorithms listed. Okay, so I'm going to be going through some of these categories and saying a little bit about some of the quantum algorithms that live within them. Okay, right. So, but before I do that, I guess I'd just like to discuss something related to near-term versus long-term quantum algorithms. So, in our fields, like people often like to divide up, what we do into NISQ, so noisy intermediate scale quantum algorithms like quantum computations, and fault-tolerant quantum computations. So, people say, okay, we're in the NISQ era now, and we're perhaps just entering into the fault-tolerant era now, as we've heard in this workshop, and we're going to be in the fault-tolerant era in the future as well. But I actually quite like a proposal from Dave Bacon earlier this year, which I'd just like to promote perhaps to a slightly broader audience, which is like, rather than this sort of divide between NISQ and fault-tolerant, we can actually have something a bit more fine-grained. And Dave suggested this nice taxonomy of KISK, MISK, GISK, and TISK, where now the ISK stands for instruction scale quantum rather than intermediate scale quantum. And now basically we're organizing by the number of gates, the number of sort of operations that are needed to execute these algorithms. And there's a couple of things I like about this. Firstly, it is more fine-grained than just saying sort of near-term or sort of long-term. But also, perhaps it highlights that, in fact, there are many different ways of getting to some of these complexities. So, for example, if we want to get to 10 to the 4 gates, 10 to the 5 gates, maybe we can do this with some sort of early fault tolerance, but maybe we can also do this just by improving the parameters of the bare gates in our quantum circuit and making those more accurate. So I think it's sort of helpful to highlight that algorithms sort of live somewhere along this taxonomy, and they're kind of always moving around. And as people come up with better ideas for the algorithms to improve the algorithm's complexity, they sort of move up the list. And of course, there are some things which perhaps it is hard to see how we could do them with sort of physically relevant sort of parameters. So algorithms with 10 to the 12, 10 to the 15 gates, it's sort of hard to see how we could do that without fault tolerance. But there is hope that some of these algorithms perhaps might move up this list further. And I guess just another point I'd like to make, which is, I guess, maybe a somewhat opinionated point, is that there aren't, I would claim, any quantum algorithms which are inherently NISQ algorithms in the sense that they only run on NISQ quantum computers. They don't make sense later on. Basically, there are just algorithms which have few instructions in them, right? Algorithms which are simple to run, and we can run them today. So that's often what people think of about these NISQ algorithms. They say, okay, this algorithm's NISQ because we can run it today. But to me, basically, this is just an algorithm that has a small number of gates in it, a small number of instructions in it. So this is something I would claim we want to be achieving for all of our algorithms. We want to be making them faster and faster. However, there are some algorithms which, again, I'm going to claim they do inherently need fault tolerance in them, in the sense that they, in order to see a speed up, they need to run for a very long time coherently, and it's just very difficult to see how to do that without fault tolerance. So an example of this is something like Grover's algorithm applied to a hard combinatorial search problem, where we need to run with a quantum circuit that is of exponentially long depth in the input size in order to see a significant performance improvement. So algorithms like this, they do seem to inherently need fault tolerance, but I'm going to claim that algorithms that use a small number of instructions are not inherently NISQ algorithms. So I think really one of the goals of a quantum algorithm designer is just to try to make everything use as few instructions as possible. Right, okay, so now I'm going to go into some of these different application areas, and the first one I want to talk about a little bit is quantum simulation, by which I just mean modeling a quantum mechanical system on a quantum computer. And there are a huge array of applications of these sorts of algorithms, ranging from like quantum chemistry, materials science, high energy physics, and perhaps biomedical science, developing new drugs and so on. And effectively any area where quantum mechanics plays a role in understanding the physical system that we care about. And just for those who may not be, quantum physicists or sort of, very, very new to this area, just to mention very, very briefly what this actually means when I say quantum simulation. So if we have a quantum system, like we can generally represent this by a Hamiltonian H. So this is, from a computer scientist's point of view, just an exponentially big matrix that happens to be represented in a very efficient way. So, for example, we might have something like the Heisenberg model, where we have a Hamiltonian H that's represented by a sum over sort of pairs of sites in some, perhaps a 1D line or like a 2D square lattice or something like this, where for each pair of connected sites in the lattice, we've got a term that looks like tensor product of Pauli X on site I, Pauli X on site J, and then identity matrix everywhere else, summed with something similar for Y and for Z, Pauli Y and Pauli Z. So the point is that each of these terms in this sum is a sort of an easy thing to understand. So this is a matrix that acts sort of non-trivially only on 2 qubits within the overall n qubit system. It's just the identity everywhere else. So this is a kind of simple thing. But then when you sum it over all of these different pairs of sites that are in our sort of interaction pattern, then we get something that's much more complicated and difficult to understand. And one of the sort of key things that quantum physicists try to do is to try to understand things like this. And there are a couple of sort of different directions, I guess, in which people often think about quantum simulation. And one of the sort of ways of categorizing is in terms of static simulation versus dynamic simulation. So static problems we might solve are problems which don't involve sort of time evolution of the Hamiltonian. There's just a sort of fixed property of that Hamiltonian. So for example, we might want to learn the smallest eigenvalue of the Hamiltonian H, which is called the ground energy to a quantum physicist. We might want to compute that up to some level of accuracy, like maybe accuracy that's sort of inverse polynomial in the size of the system. And this problem is known to be QMA complete in the worst case. So this is the quantum analog of the complexity class NP. And this means that we think that in the worst case, it's very hard to solve this problem, whether for a classical computer or a quantum computer. Right? However, many practically relevant cases may turn out to have efficient algorithms for this task. So this is exactly the same as with classical constraint satisfaction problems, where in the worst case, instances of 3-SAT may be very hard to solve, but in many practically relevant cases, we can actually solve them. Okay. So that's static simulation. We could also consider simulation of the time dynamics of a quantum system. So, for example, we might want to compute like e to the minus IHT, which corresponds to time evolving according to Hamiltonian H for time t, and just compute this particular entry of this matrix, again up to perhaps inverse polynomial accuracy in the system size. And this problem's BQP complete. So this means that you can do it with a quantum computer efficiently, and in fact, anything that you can do with a quantum computer is reducible to this problem. So this is sort of interesting that you've got this dichotomy between these two problems. Right. And so, like I said, even though we think that computing ground states may be very difficult in the worst case, in practice, it may turn out to be kind of easy. We don't know. It's something we need to try for each given instance. And there's a number of different approaches that people have developed to really try to do this. One of them, which is very famous, I guess, and well known, is the variational quantum eigensolver, or VQE. And what we do in this algorithm is we have a family of quantum circuits that we sort of fix in advance. And that family has some parameters in it. Maybe the family sort of depends on the particular Hamiltonian we're looking at, or maybe it's something that's more generic than that, and maybe it's kind of connected to the architecture of the quantum computer that we're running on, or something like this. But anyway, it's a parameterized circuit. And what we want to do is we want to find the optimal parameters within that circuit such that we minimize the energy. So we apply this quantum circuit to some initial state, then we measure the energy with respect to the Hamiltonian, and then which is something we can do with a quantum computer. And then we want to classically optimize over the parameters of that circuit to find a good set of parameters to make that energy low. And there's been a huge amount of work on this, ranging from some theoretical work, but also many sort of numerical and experimental implementations of this. There are a number of challenges that VQE faces, which I'm not going to go into today, I guess. But again, I think it sort of nicely fits into this category of these sort of heuristic algorithms where, to really understand how well the algorithm performs, you probably need to just run it. There are a number of different approaches as well. There's something called quantum imaginary time evolution, or KITE, and related topics to that, where effectively what we try to do is we try to approximate an operator which sort of which gradually goes down to the ground state of H. So we want, like, if we could actually implement this non-unitary operator here on some initial state, then this will eventually, if we do it enough times, depending on how big this delta is, this will eventually get us down to the ground state. And this is not unitary, so it's not obvious how to do this on a quantum computer, but we can try and find a quantum circuit that somehow approximates that operator, which is something that's worth trying. There's also, again, one of the earliest papers in quantum computing, which is an adiabatic evolution, so it's the quantum adiabatic algorithm. So in this approach, we imagine that we start out in the ground state of an easy Hamiltonian, so it's something where we can easily prepare this ground state. And then we gradually change the Hamiltonian from easy to hard. And then the quantum adiabatic theorem says if we do this slowly enough, then we are going to remain in the ground state throughout. So we end up producing the ground state of the final Hamiltonian. And the question of how slowly is slowly enough is a sort of difficult one, but again is something which in some practically relevant cases, or maybe in many practically relevant cases, may be relatively efficient. And just to mention something a bit more recent, so this is some work done by my colleague Toby Cubitt at Phasecraft, which is the dissipative quantum eigensolver. So basically, the rough idea behind this is that we again start out with a sort of arbitrary state, and then we perform some sort of weak measurements to gradually project down onto the ground state. So, it's sort of intuitive that if you have your original Hamiltonian, then if you sort of measure each term in the Hamiltonian and you end up sort of in the ground state, the ground space of each of the terms individually, then this should kind of get you closer and closer to the ground state of the overall Hamiltonian. And it takes a bit of work to make this intuition kind of precise. And in particular, it turns out that you don't want to just project onto the ground state of each one after the other. You want to do something a bit sort of weaker and more controlled than that. And also you have to decide when you want to stop this process. Like you sort of do these weak measurements and then you see some sort of positive outcomes, some negative outcomes, and you sort of stop after you receive enough positive outcomes. And there's some work that goes into deciding when to stop. But again, one can show that this effectively works. And it may take a very long time, but it does work in the end, and you will eventually get to the ground state of your quantum system. So, there's obviously a whole slide here about different approaches to producing ground states, and there's a bunch more of them as well. And you might wonder, like, why do we even care about producing ground states? If you're not a quantum physicist, you may wonder this. And one reason is that we can use these things directly. We can use the ground states, the ground energies, directly to get useful information. So, one concrete example that I like is that just given the ability to compute ground energies of a particular family of material systems corresponding to cathodes of lithium-ion batteries, you can compute the voltage profiles of those batteries. So you can understand how the voltage changes as the battery discharges just by computing these numbers for different Hamiltonians. And there's many other physical properties you can also get directly from this. So there's many practical applications as well as being theoretically interesting. Okay, so that was static simulation, but we can also do simulating time dynamics on a quantum computer. And this is an interesting one because in a sense, it's almost the converse of the static case in that these sort of algorithms are efficient in principle in that there are many algorithms that run in time polynomial in the size of the system that we're wanting to simulate. But many of these algorithms turn out not to be quite as efficient in practice as you would like. And a lot of work has gone into making this as efficient as we possibly can. So, just to recap, we want to, when we do time dynamic simulation, we want to implement the unitary operator e to the minus iht for maybe, let's say, a Hamiltonian that has some locality properties in it. So some Hamiltonian H, which is a sum of terms that only act non-trivially on most k qubits each. And there's many different approaches one can follow. And one of the earliest ones is product formulae. So if we have something like e to minus IHT, then we can approximate this as a product of terms, each of which is time evolution according to one of the terms in that sum. So this, in general, like each of these HJs, we're imagining we can implement this time evolution efficiently and sort of easily. Maybe it only acts, as I say, non-trivially on just a few qubits, so it's easy to implement this operation. And this is first order Trotter formula here, which many of you probably are familiar with, which says that if you choose this sort of delta to be large, then if you repeat time evolution by each of these terms for a small amount of time, and then you repeat this whole thing, like delta times, you end up approximating like time evolution according to the whole thing. So this is one thing you can do, and there's been a lot of work since then on developing more advanced and complicated, more high performance product formulae for doing time dynamics. So you can also think about other ways of approximating the exponential function. So one that I think is very nice is Taylor series-based methods, where in a sense, I guess it's maybe if one didn't know anything about quantum mechanics, it's sort of the first thing you try. Maybe you sort of think, okay, so I've got e to the minus AHT. I'm going to expand this in terms of its Taylor series, and I'm just going to truncate at some order, and now I'm going to try to somehow simulate this remaining operator that I've got here. And the thing that's tricky to see about this is, like, this is now a sum of some operations. Like, in fact, it may not even be unitary operations here. Like, in fact, generally, you can take this you can take this to be unitary. Well, okay, sorry, I should be clear. So this now, I ought to really expand this over these different terms as well to really see how this ends up working. But basically, if you do this, you end up with something which can be taken to be a linear combination of a bunch of unitaries, and then it turns out that you can implement these linear combinations of unitaries pretty efficiently as well. So if you combine these kind of ideas, you can get also an efficient time dynamic simulation algorithm. There's a very beautiful family of works related to so-called quantum signal processing or qubitization, which I definitely don't have the space to do justice to here. But the very basic idea behind them is that we imagine that we have our Hamiltonian H, and we fit this into a unitary matrix as a block within that unitary matrix, a so-called block encoding. And then it turns out that we can implement functions of that Hamiltonian H that's been stuck into this unitary matrix as a block in very nice ways. So in particular, we can implement Chebyshev polynomials of this H in a very nice way involving sort of quantum walk type operations. And this enables us ultimately to implement arbitrary functions of H, and in particular this time evolution operation. But there are many other techniques known as well. Okay, so I said that I'd try and include some real numbers, and I thought maybe it's helpful at this point to do that for this particular case of time dynamics simulation. So these are numbers that's taken from a recent paper that I'm a co-author on at Phasecraft, where we were looking at trying to develop more efficient time dynamics simulation algorithms based on product formulae. And what this graph is showing is the 2-qubit gate depth you need to time evolve for a particular quantum Hamiltonian, this Ising model with transverse field, which looks like this. So this is just the 1D Ising model with transverse field, which is actually efficiently simulable classically, which is one reason why we're able to do this calculation and do these numerics up to quite large sizes. And this graph is plotting for different algorithms the number of the 2-qubit gate depth that you need in order to evolve for time L for a system of size L with error 0.01. So that's achieving, I think it's probably operator norm error in the end, that between the approximate algorithm and the algorithm you're running and the ideal time evolution. And what you can see is that, depending on which algorithm you use, and this one at the bottom obviously is our new algorithm, but depending on which algorithm you use, you can get something from like 10 to the 6 gates down to about 10 to the 3 gates. And sorry, this is 2-qubit gate depth, right? This is not total number of gates. But basically, these are all different product formulae algorithms of different sort of orders. I'm not going to go into all of them. But basically, I guess maybe a take-home message of this is that the choice of which time dynamic simulation algorithm you use could easily make a factor of 1,000 difference in what the gate complexity is. Yes, sorry, please go ahead.
Right here, do you consider this is just the total number of gate, but how do you come to the depths? Because
this is the depth. I'm sorry. So this is the 2-qubit gate depth.
Depth. Okay, not the constant.
Yeah. But I mean, the circuits, to be honest, the structure is such that the number of gates is very closely related to the depth, because at each layer you have a very sort of dense circuit. Okay. Yes. Oh, sorry. Yes. Go ahead.
So do you fix the error and then about the number of gates, and is that like the actual error achieved, or in practice is it much smaller error?
Oh no, this is actual error, right? So this is sort of numerically, this is not sort of theoretical bounds, and so this is saying, let's say you want to achieve error 0.01. This is the gate depth that you need in order for the algorithm to give you that error. So I should say that there's some previous work by Andrew Childs and co-authors which did a sort of similar analysis with for the 1D Heisenberg model with random local fields, which in fact we also do it in our paper. You can see it if you're interested. And they found in that work, that numerical bounds, often there is a bit of a gap with the theoretical bounds. And they also found there that these more advanced algorithms that I mentioned on the previous slide turn out not to be so competitive with the basic sort of product formula sort of trotter type algorithms. So so that's why in this plot we're only considering those product formula type algorithms.
Yeah, please. I think I missed it. How are you connecting time L with system size L?
Okay, so we're just saying, okay, we want to evolve for time L for each system of size L. The idea being that this is a sort of interesting time to evolve for, because you're sort of seeing the full system at that point. If you're evolving for a much shorter time, then you would expect perhaps that the depth maybe won't scale with system size. Oh, sorry, please.
So do you anticipate that Trotter formulas will be cheaper than these fancy LCU and USP?
I'm not sure. I wouldn't make that claim for all Hamiltonians. I would say that for these sort of spin Hamiltonians with a very simple structure, I mean, okay. So I think in these experiments we didn't compare these fancy methods, but to be honest, I would be very surprised if they are competitive, because in this previous work, which was looking at very similar sort of Hamiltonians, there was really quite a gap. But for more complicated Hamiltonians, like let's say like quantum chemistry ones or whatever, then I guess I wouldn't know one way. Okay, cool. Thanks for these questions. But yeah, I'm going to move on to something totally different now, which is just going to be a very brief interlude actually, because I guess I don't have a huge amount to say about it. But obviously it's sort of very well known that one of the most prominent applications of quantum computing is breaking classical crypto systems. And I guess I just wanted to sort of make a few sort of key points here, which are not always well understood, which is that firstly, many crypto systems are known to be vulnerable to quantum attack. It's not just like an RSA crypto system. Secondly, not all crypto systems are vulnerable to quantum attack. Like there are some that we don't know if there's an efficient quantum algorithm to break them. And I've just put a few examples of crypto systems on here, and how they might be connected to quantum computing. I mean, obviously, one that many of you have probably seen is this recent excitement about can quantum computers break lattice-based crypto systems, with this paper of Yilei Chen that came out recently. And I guess like this is the latest in a few papers that have tried to break lattice-based crypto systems with quantum algorithms. And I think it's a very challenging, very technical area. And papers in this area have often had bugs in them. And as I understand it at the moment, that seems to be the case with this paper. But I think for me, what this sort of really highlights is that this world of post-quantum crypto is, I would argue, on somewhat shaky foundations, in the sense that there have really not been that many people who have been working on these sorts of questions, and it's always possible someone can come up with a bright idea that does attack one of these crypto systems. Sorry, question? Oh yeah, sorry, Peter.
Yeah, my impression is that a Mac-Release crypto system is not a single crypto system, but is a different crypto system for each class of error-correcting codes, and breaking it on one of these classes of error-correcting codes has no no, no impact on all the other classes of aircraft.
I think that sounds very plausible to me. I mean, I suppose, it's not ruled out there could be a quantum algorithm that breaks all Macaulay-based crypto systems, right? But I would be surprised, but because I mean, ultimately, there is there's an abstract problem of like, sort of code equivalence or like, decoding this sort of randomly permuted code, right? But I mean, personally, I think it's very unlikely there is a quantum algorithm that does this, but I suppose it's not.
Well, decoding a binary code is, at least for some parameters, an NP-complete problem. So if you could, so my impression is if you can break Macaulays for all codes, then you can solve an NP-complete problem. But maybe I'm wrong about that because maybe the parameters are different.
Well, okay, but you've also got the fact that you have this sort of hidden permutation like aspect to it. So maybe you can use that in a clever way. I mean, I don't know.
I mean, if we're speculating, you could imagine a theorem that says, okay, whenever a code is useful for a Macaulay-like crypto system, then this quantum algorithm breaks it, right? And it wouldn't solve the problem of can public key crypto be based on NP hardness, right? But
yeah. Okay, and again, maybe many here are familiar that there is this entire field of post-quantum cryptography where the goal of the field is to develop crypto systems that are secure against quantum attack. And the thing I found sort of amazing to realize when I was preparing for this talk is that the NIST process for standardizing post-quantum crypto has been running for 8 years now and it's not finished yet. So I think this sort of highlights how sort of challenging it is to do this and like how much time it takes to actually move to a different crypto system. And even once the crypto systems are standardized, they still need to be rolled out and so on. Okay, so then people often wonder, okay, even if RSA is in principle breakable using a quantum computer, like is this really realistic in the near term? And people are still working on improving these bounds, and it maybe actually even results during this conference have improved this. But one nice example where this analysis has been done is this paper of Craig Digney and Eckero in 2019, where they show that if you have 8 hours and 23 million physical qubits, then you can break RSA 2048. So this is, I guess, like not unreasonable if you have a fault-tolerant quantum computer. I mean, maybe you're happy to run it for 8 hours to break RSA, but really, I mean, that's obviously some way off what we have today. Okay, so I'm really already running out of time, but I just want to get onto a couple of different topics still. And the first one I guess I want to consider is search and optimization problems. So unstructured search is really one of the most basic problems in computer science. So we might imagine we've got access to some function which we're going to treat as a black box. It's just we pass in n bits and we get 1 bit out, and we want to find some x such that f of x is equal to 1. And this is something which, classically, in the worst case, it's sort of clear it's going to take us about 2 to the n queries to this function f to solve it. But on a quantum computer, then we can use Grover's algorithm to solve this with square root of 2 to the n queries to f, and with maybe 99% successful. And people often, I guess, wonder, like, does this actually give us something which is sort of practically relevant? I mean, this seems like a very abstract problem. Unstructured search seems like a very sort of naive classical algorithm. Are there cases where we could genuinely expect to use Grover's algorithm to see an advantage? And we can apply Grover's algorithm whenever we have a problem where we can verify the solution efficiently. So if there's any problem in NP. And one nice example where we can apply this is to the circuit SAT problem. So here we've got a circuit it takes n bits as input, and it spits out 1 bit at the end as output. And we want to know if there's an input to the circuit such that the output is equal to 1. And in fact, the best classical algorithms we have for this task take time roughly 2 to the n, like they scale like 2 to the n. And Grover's algorithm can solve circuit SAT in time 2 to the n over 2 up to constant factors. So you can see already there might be applications of this kind of thing in electronic circuit design, like maybe checking if a circuit's got faults, or automating design of electronic circuits, checking if circuits are equivalent, things like this. And beyond this sort of simple algorithm of unstructured search, we can also accelerate many other algorithms in classical computer science. And often what we see with these speedups is they're quadratic kind of speedups. So we can speed up our classical algorithms based on primitives called backtracking or branch and bound. So this is sort of trial and error classical algorithms where we want to find a solution that maybe satisfies some constraints. And we start out by assigning values to some sort of bits of the solution. And then if we find that the solution already violates some of the constraints, then we sort of give up on that path and we go back a bit and try something different. So algorithms like this, we can also get a quadratic speed up quantumly via a method using quantum walks. We can accelerate some classical algorithms based on dynamic programming, which is this really nice classical technique, which is maybe familiar from introductory algorithms classes, where we build up a solution to an overall problem by combining solutions to sub-problems in a nice way. We can speed up many classical algorithms that are based on rapidly mixing random walks with quantum walks, and these again often give a quadratic speed up. And then, these sorts of subroutines then have a bunch of applications in turn. So just a couple of examples I just want to highlight are, we can speed up algorithms for solving the traveling salesman problem for certain graphs, which, these ones turn out to be based on this sort of branch and bound approach. We can find short vectors in lattices, not breaking lattice-based crypto systems, but achieving a improved complexity compared with the classical algorithms, so a sort of square root runtime. And many other things. But these algorithms have some particular features in general, which are sort of, which are real sort of challenges for implementing them. So in general, these general purpose algorithms achieve at most a quadratic speedup over their corresponding classical algorithm. And they tend to need very deep quantum circuits. So they tend to sort of work by kind of building up amplitude over the course of a very, very long circuit, which generally needs to be exponentially long in the problem size. So it seems hard to do them without using fault tolerance. And given that there's a significant overhead from error correction, this causes a problem for these algorithms. So, for example, one analysis that we did a few years ago looked at trying to solve hard graph coloring or satisfiability problems. And we were interested in problems that could be solved in at most 1 day on the quantum computer, making some sort of assumptions about the clock speed and so on. And it turns out that for problems like this, compared with a classical desktop PC, so not compared with a supercomputer, but a standard sort of desktop, we might see some kind of, based on our analysis, we might see some kind of speed up. So maybe of the order of factor of 10 to the 5. But this is with a gigantic amount of physical qubits for doing the error correction. And sort of even worse, if you take into account the cost of the error correction processing, then the advantage ended up disappearing entirely. So the conclusion we took from this is that speedups might be possible using these methods, but we're going to need really big improvements in the error correction machinery. But there's an even more pessimistic view actually from this paper of the team at Google in 2000, where they do a more detailed analysis and get even more depressing numbers. So this then sort of raises the question of, can we actually solve optimization problems or constraint satisfaction problems in the near term using quantum computers? And one way in which we can try to do this is an approach called the quantum approximate optimization algorithm, QAOA. I think we'll have a whole talk by Eddie about this later, but I'm just going to give a very brief intro to it. And this can be seen as applying the VQE framework, the variational quantum eigensolver framework, to classical optimization problems by considering a Hamiltonian where for each computational basis state x, we have an associated cost C of x, which is on the sort of diagonal of this matrix. And then we're looking to find the ground state of h, which is the same as the lowest cost bit string x. And if this cost function C is of some nice form, like maybe it's a sum of some sort of costs of which only depend on small parts of the problem, then we're going to get a local Hamiltonian out, which maybe means that we can hope that this variational sort of approach might end up finding a good solution to this. And Eddie Voigt, co-authors, proposed the following method. So we start with a uniform superposition. Then we apply time evolution according to the Hamiltonian h for some length of time, sort of gamma. Then we apply this sort of mixing unitary, which depends on this parameter beta. And then we repeat this procedure like p times. So we do this a certain number of times. And the parameters that we do this time evolution for beta 1 through beta p, gamma 1 through gamma p. These are ones that we can optimize using the quantum computer itself. So we can compute sort of energies, we can compute sort of costs based on each given choice of parameters, and then we can try and minimize the cost. So this, this has a hope of sometimes giving us, good answers, even when p is quite low, even when p is maybe even a constant or maybe low. And this, a very similar algorithm was described by Tad Hogg back in 2000. I guess the key difference is that this algorithm had a fixed choice of the parameters and did not include any variational optimization. Okay, and how well does this approach work? So hopefully Eddie won't disagree too much with what I'm going to say on this slide. So I would say that precisely how well this performs on a given problem is generally hard to determine. So sometimes you can, but not always. It's known that if you have many, many layers in QAOA, then the algorithm can reproduce the performance of Grover's algorithm. So it's sort of no worse than Grover's algorithm in that sense. And we also know that even if you have one layer in QAOA, that it's hard to simulate sampling from that, the distribution it produces. In many cases, we can analyze the performance of QAOA on optimization problems. Like we can work out, if in some cases what the fraction of constraints is that it can satisfy, like its approximation ratio. And often the bounds that are found tend not to outperform the best classical methods in terms of the fraction of the constraints we can satisfy. We can also apply QAOA to constraint satisfaction problems, like rather than optimization problems. We can run the algorithm and we can try to use it to produce a solution to a bunch of constraints. And it turns out, if we do, you can analyze the performance of QAOA in this context as well. We did this in this work and applied this to random KSAT. So we have a Boolean satisfiability instance with k variables per clause, and we're choosing this at random at the sort of hardness sort of threshold. And we were able to theoretically and numerically analyze the performance of the algorithm, and the scaling of this seemed better than the best out of classical algorithms we could find. So there is maybe some hope that QAOA outperforms classical methods in these contexts. Okay, so the last thing I want to mention very, very briefly is a sort of whole, again, different area of quantum algorithms research, which is using quantum algorithms to solve linear equations. And this is sort of very natural because really what goes on in the quantum computer is exactly high-dimensional linear algebra. So it's interesting to think, can we use quantum computing to solve large systems of linear equations directly? So, the basic problem we might think about is we're given a matrix A and a vector B, and we want to output X such that AX equals B. And quantumly, we can think of this as follows. We imagine we've got the ability to produce a quantum state corresponding to B, like a superposition corresponding to B. And we have the ability to sort of query entries of the matrix A. And then we want to produce a state corresponding to X, which is a superposition of the same sort of form. And Aram Hara and co-authors showed back in 2008 that if the matrix A has bounded condition number kappa, then we can approximately compute X in time that's polynomial in log of the size n, the sparsity d, and the condition number kappa. So this is exponentially better than what you could do classically, because classically, even to sort of write down all of the equations is going to take you time polynomial in n. Okay, so there's a number of caveats that go into the algorithm, which are sort of well known, and one of them is this thing, like it produces a quantum state X, which is a superposition corresponding to the output. It doesn't give us all of the output itself. Even to write down the whole output would take us time n. So we have to think about, okay, can we actually do something useful with this? And one sort of thing we could do, for example, is determine whether two sets of linear equations have approximately the same solution by taking the sort of inner product between these vectors. And this was, I think, an observation of Andreas Ambinus from a long time ago. And also, this linear equation solving is known to be BQP complete. So if we could achieve a similar runtime classically, then actually we can do all of the other things I talk about today using classical computation. So it'd be sort of surprising if we can completely dequantize this algorithm. People have tried to apply it in many ways, and there's only a few I guess I'm going to put here. And these are all a bit out of date now. I think there have been a lot of recent works as well. But I guess the overall point I'd just make is that one tends, like in all of the cases, I think on this slide, so far, there were sort of apparently exponential speedups using these linear equation solving algorithms, which then tended to sort of go away later on. So, for example, one thing you might try to do is use quantum linear equation solving to solve large systems of PDEs by sort of discretizing that system and then solving the corresponding system of equations. But you have to be pretty careful there, because it may turn out that, because effectively what the quantum computer gives you is the ability to discretize much more finely than you can do classically. But it may turn out that classically you don't need to discretize that finely, and you can do quite well with a sort of simpler algorithm. So that's one potential issue. And also there's been some, this whole series of great work started by Yuan Tang on finding quantum-inspired algorithms that somehow dequantize some of these key aspects of the quantum linear equation solving algorithm for some particular applications, for example, recommendation systems. So, in some of these cases, you may be left with still a polynomial quantum speedup, not an exponential one. So it may still be a sort of valuable subroutine, but it's just something where you need to be careful.
Actually,
yeah, sure.
What's the current situation with the electromagnetic scattering cross-sections?
I think, okay, I may be wrong, but I think already in 2015, when we did this work, like it seemed that there was at most a polynomial speedup.
I see.
Unless you want to do electromagnetic scattering cross-sections in like 100 dimensions or something.
Or like for some weird implicitly constructed object that encodes Shor's algorithm.
I guess. I mean, basically, at an extremely high level, the issue with using HHL or similar approaches for many of these problems is that if you have a fixed number of spatial or time dimensions, then you, like classically, if you want to discretize this system up to accuracy epsilon, you can do it with like a problem of size like 1 over epsilon to the d, right? So just and right. All these finite element methods, they can achieve that basically. Yeah. So the classical runtime is generally not worse than 1 over epsilon to the d, and the quantum runtime is not better than 1 over epsilon squared or something like maybe 1 over epsilon. So
thank you.
Yeah. There may have been some more recent work, but this is what I know. Okay, so I'm already running over a little bit, so I'm sorry about that. But
if you need a few more minutes, I will have
okay.
questions.
Good. Great. You shouldn't have said this. No. I am getting to the end, but I sort of, again, as this is a conference, there's sort of trying to think about, the sort of near-term world. I wanted to have some actual numbers of gate counts for some particular applications, and we can so people can see what they think about how near-term perhaps some of these things look. And the applications that I've put up here are all ones that are related to quantum simulation, because in many cases some of the other applications seem to be a bit further off, or perhaps it's difficult to analyze how well the algorithms perform. So what I've put here is a few examples where I've put a number of algorithms which are sort of one layer of a VQE algorithm, or perhaps a sort of trotterized time dynamic simulation for a few different physical systems. So like these, in fact, I think these ones all came out of work that we did at Phasecraft. I'm happy to give you references if you're interested. But basically, so this first one is looking at this famous Fermi-Hubbard model in condensed matter physics, and looking at how many gates you need to implement sort of one layer of a particular variational ansatz, which also happens to correspond quite closely to time dynamics simulation for this model of size like 10 by 10, which is beyond the ability of classical exact diagonalization, although perhaps not beyond the ability of tensor network methods. Also, something similar, but for a sort of realistic, more realistic materials system called strontium vanadate. Similarly, looking at the Heisenberg model on a particular lattice, the Kagome lattice on 100 qubits. Then also, time dynamic simulation for a couple of different models. Like one of them is this result I mentioned earlier in the talk, Ising model, but now with a slightly weaker field, which makes it easier for the algorithm. And also this Fermi-Hubbard model. And what we can see is that, this one, which is a sort of simple spin model, is a bit sort of easier, but in general, we have sort of complexities in the thousands or tens of thousands for this. And it's maybe interesting to compare against where we are today in terms of the number of gates used in some benchmarking experiments. Now, I know that the authors of some of these are in the audience, in fact, maybe all of them. So I'm sorry if I made any mistakes with these gate counts. Please do correct me if you happen to remember the numbers and these are wrong. But basically, what we can see is that a number of gates that we have in these kind of experiments, it's now in like the high hundreds or sort of low thousands. And for me, I have to say this is pretty impressive when you think that a few years ago people were running experiments with 22 qubit gates, and that was pretty exciting. So so it's so depending on whether you're an optimist or a pessimist, I guess you can sort of say, okay, there's still a gap between this and this, or you can say, well, actually, some of these numbers are relatively close to the numbers here, or even bigger than them in some cases. So this is one reason why I think actually we are getting into a really exciting era for experimental implementations of quantum algorithms, because many of these applications really are either sort of achievable now or sort of in reach in the near future.
What's TDS again?
Time dynamic simulation.
Let's perhaps give Ashley the time to wrap up. And then
Yeah, so time dynamic simulation. But yeah, this is indeed my last slide. So I guess I always make a phrase like this when I give a talk on quantum algorithms, because you still see claims like in the media and so on that there are 2 quantum algorithms or something like this. And I think this hasn't been true for a long time, and actually there are now hundreds of quantum algorithms solving a number of really interesting problems. But there's a lot more interesting questions out there that we can try to address. And I just put a few suggestions there. Like obviously it's very nice to find more applications for some of these algorithms. There's many cases where we have an algorithm which we have sort of good asymptotic bounds in its performance, but maybe not exact analysis of its complexity, including perhaps fault tolerance overheads. It's really important to come up with new ideas for developing quantum algorithms. And I think, in this talk, I've mentioned, a few cases where there are, totally different concepts that go into algorithms for a similar problem. And I think this is still a very interesting direction in the future. And also something which I guess is dear to my heart at the moment, which is, how can we actually do interesting things on near-term quantum computers and get the most out of those? So, I just want to finish by listing a few references. Some of these are old now. So I guess, I have this sort of survey paper on quantum algorithms, which is 9 years old now. And I think this is only now of interest for historical, reasons, because you can see like how little there is of the things I talked about today that's actually in that short survey. There are some very nice tutorial talks by Andrew Childs I'd like to particularly highlight, which talk about a lot of the things that I mentioned. I guess, as a tradition, I'd like to finish with an advert and say that we are currently hiring at Phasecraft. And if anyone's interested, please just come and chat to me. That's it. So thanks very much.
thank you very much, Ashley, for very efficiently solving the impossible task we gave you to give the overview. Perhaps there's time for 1 or 2 questions. Yes, please.
The last table that you actually showed, so maybe I'm confused, but when you mean about the layer of DQ, so you mean about the ground state vibration or the time vibration, and those numbers will also strongly depend if you're looking in 1D, 2D, what kind of lattice you're looking. So I'm a bit confused why we would compare all of those numbers together in one.
Well, okay, so these numbers are all for this particular variational ansatz, which is called the Hamiltonian variational ansatz, and this is saying what's the cost of doing 1 step of that variational ansatz. That does not mean it will produce the ground state. In fact, in general, it won't. You'll need a number of layers, and the number of layers you need is actually not obvious in advance. But the point is, and you're right that the complexity does depend on what the lattice looks like. So here, I've given 2 particular cases. So this is the Kagome lattice. So this is a 2D lattice, and this is like 10 by 10 square lattice. And then this one in the middle is more complicated. We can discuss if you're interested. But yeah, so the complexity does depend on this. But these are some concrete numbers for particular cases.
All right, then that's one last question.
Yeah, thanks for the nice talk. Like maybe one follow-up on this is also, so I think it's useful to think about like the instruction set based regime, but like in this table, like the target gate sets for different instruction sets would probably be different. Like you talk about 2 qubit gates here, but say if you're thinking about a fault-tolerant like regime, like doing T gates and arbitrary rotations would be hard, and like that would have an additional cost. And I believe like if you're thinking of this in terms of NISQ, then Like, are you also thinking of like specific hardware and routing costs? Or
Yes. Okay. So so just to have a simple metric where you can compare different things. I just like here. I'm just thinking of raw 2 qubits gate count, and like I think not even fixing particularly sort of CNOTs or something like this. So it's true. Like if you have a fault tolerant architecture, you want to think about things like T gates instead. I think the numbers will not end up being significantly different in many cases because, like. In general, so like for example, if you have maybe I'll just take a particular example like this sort of okay I would say it depends. Okay, the thing that may change when you go to fault tolerance is that if you do just have like Clifford plus T, then maybe you just need a lot of T gates to do your sort of approximating a thing. So yes, that's right. So if you think about that, the numbers do get a bit worse. But I think that's probably the key.
All right, then in view of time, I would suggest to postpone the remaining questions to the coffee break and then reconvene after the coffee. Thank you very much again, Ashley.